Kia ora koutou. This is an AS question for Ben, and it's a really good integration problem. There are 3 parts to the question, but I'm going to ignore the first couple and just quickly give you the answers for those. So we've got a curve and we've got a straight line, and we've got a nice diagram showing those 2 things. And you can probably just about guess what the first parts of the question are going to be. We're going to have to figure out the coordinates, or just the x coordinate, of point B and point C, which are the intersection points. So we've got this linear function and this curvy thing, and we have to figure out where they meet. So for that one, you're going to end up getting 1 here and 9 here. And to do that, you end up with a disguised quadratic. It's not too bad. It's just a pretty standard 4-mark algebra problem. And then we have to show that B is also a stationary point on the curve. So B is this point here. We do that by finding the derivative of this and showing that when x is equal to 1, dy by dx is 0. So I was going to go right through those, but I think this is going to get long enough anyway. So the more interesting part is that we have to find the area of that shaded region. And I want to go over a couple of basic things about the difference between an integral and an area. So I'm going to hop over here, and hopefully the stylus is not going to melt down like it just did when I tried to do this. So here are my axes. Now, when we start with integration, we have some function here, and we have limits here. And that area is sitting above the x-axis, right? And so the area between, the area that I've shaded in there is simply the integral of f of x dx, and that's all good. The area and the integral are the same thing. Then the next thing, well, one of the things that we learn next is, suppose now, let's just extend my axes down here. Right, now, if you're watching this for A-level and you're finding this too slow and boring, that's fine. Just make sure that you really do understand it. So here's my function now, and my function now is below the x-axis. So suppose that I want to find that area. Well, when I integrate this, that integral is going to be negative. So if I want to find the shaded area, area is always positive. We have to take the absolute value of this. Okay, and we get quite used to doing that. Where we've got to watch out is where we're changing between above and below the axis. So this is kind of like big red flashing light thing. So suppose that we have to find, oh, I think the pen's stopped working. Oh, there we are. Suppose that we want to find the area A plus the area B. Well, we can't just integrate from here. Suppose that's 1 and that's 10. If we try and find this, we're going to go wrong, because we're going to get, it's not going to take into account correctly the above and below bits. So we have to break that problem into 2 bits. Okay, so we're going to find this bit, this area here, and we're going to find this area here. Okay, a good thing that happens is that if instead I've got 2 functions, and we're going to use this in Ben's question, suppose I've got f of x here and I've got g of x here. And if I want to find the area between those 2 things, then it's the top one minus the bottom one, dx. Now, it's pretty obvious that that's going to work here, because what we're really doing is saying, well, the f of x area will be all of that, right? So that's what happens when we integrate that. And then the area under the curve here is this bit that we're taking out here. What's really nice though is that if we've got, suppose we've got f of x like this, and we've got g of x like this, then the top curve minus the bottom curve is still going to work. We don't have to worry about the fact that this one, g of x, is below the curve. And I think it's pretty intuitive that that works, because we could just take that whole thing and we could just move everything up by k units, right? So if we do a shift of the whole thing upwards, then the area is not going to change. Right, so all of that brings us back to what the actual question was here. The other thing that often comes in handy when you're working with harder integration problems is that if you can use the area of a triangle is equal to half the base times the height, that can quite often give us some good options for these problems. I put this diagram in twice because I'm going to do this question in 2 different ways. You can see that I've already used up 5 minutes and I haven't actually integrated anything. So the first way that you can do it, and the way that I did it when I first saw it, is that I looked at the two curves, and I could see that this point is 4, this point is 3. And so I can use my area between two curves thing, f of x minus g of x dx, evaluated between 9 and 4. So that's going to get me all of this, and that's going to be pretty easy, nothing hard about that. But then I've also got to add in that little baby triangle there. So it's going to be the triangle area plus that. Okay, so that's the first way to do it, and I'll go through that in a second. And then the second way to do it, which is how the mark schedule did it, which I really liked, is that the mark schedule just said, well, we've got one big triangle here, right? So let's just flip this around here. Let's draw in this. And so you can see that this triangle here is very easy to find the area of. So the area is going to equal the triangle area. And then I'll try and shade this properly. We're just going to take out from that. Oh, I'm not drawing within the lines. Sorry, guys. I'm sure that's annoying some of you. There we are. We're going to take out that green shaded area. And that green shaded area will be, it'll be the absolute value of the integral from 9 to 4 of 4 root x minus 2x dx. Right, now it's going to be the absolute value because this integral, because it's sitting below the axis, is going to be a negative number, right? But we want to take it away. We want to take away the positive number because we don't want that area sitting in this triangle here. So I'm going to do both of those ways now. Actually, I'd like you to pause this video and you try both of those ways first, and then watch me go through it. And the answer we should get for both is 11 over 3. Okay, so the first way, let's get rid of all of this. Well, the little triangle here is a half times 1 unit across and 1 unit down, plus the integral from 9 to 4 of 4x to the half minus 2x minus 3 minus x dx. I'll just get rid of that mess over there. So I'm going to clean up slowly. I've got 1/2 here, plus the integral from 9 to 4 of 4x to the 1/2. Now I've got minus 2x here, plus x here, gives me minus x here, minus 3 dx. And I'll stick that in brackets. So working this through, we've got the 1/2 from my triangle, and now we're going to anti-differentiate. It'll be x to the power of 3 over 2. We've got 4. We have to undo the 3 over 2 with 2/3 minus 1/2 of x squared minus 3x, and that's evaluated at 9 and 4. Now this is quite good practice at thirds. So quickly going through this, we've got a half plus, right, 8/3 times, right, x to the power of 3 over 2. Well, the square root of 9 is 3. 3 cubed is what we want there. Minus 1/2 of 81 minus 27 minus, and now off we go again with 4. So it's going to be 8/3 of, right, 4 to the power of 3 over 2 is the square root of 4, 2. 2 cubed is 8. Right, minus 1/2 of 16 minus 12. Right, so a wee bit of cleaning up here. We've got a half plus, right here we've got the 3 cancelling out with that. So we've got 72 minus 27 minus 40.5 minus 64 on 3 minus 8 minus 12, which gives me minus 20. So we've got 0.5 here. 72, 31.5 minus 27. That gives me a half plus 4.5 here minus 64 on 3 minus 60 on 3 gives me 4/3. So it's 5 minus 4 on 3. Yes, I know you're going to bung that in your calculator, but let's just check. So 11, let's see, 5 3s are 15, so we get 11/3. So that's doing it that way. Now let's look at it the other way. So remember, the other way is using a big triangle and then taking out a cleaner interval. So the second method is less work, right? It's slightly less integration. there are slightly fewer chances for making sign errors. So I really like it. I prefer the marked schedules way to my way, but I still think there's probably things to learn from both. Okay, so here, this big triangle has got an area of what? Well, that's 3 and that's 9. So the full area here is going to be half times the base, which is 6, and the height is 6 as well. Right, now I know the height's 6 because the slope of that line is -1. So it's going to be that. And then I'm going to take out the area between the x-axis and that curvy bit. So this is going to be the integral from 9 to 4 of 4x to the half minus 2x dx, right? And I'm whacking in those absolute value signs because I know that this is going to be a negative number, and I know that I'm going to screw up if I take away a negative number because I'll be adding instead of taking it out. So we get a half of 36, so 18 minus, and here we get 4, the same thing again, 4 times 2/3 of x to the 3/2 minus x squared. So that whole integral is easier, right? Let's clean this up here. Okay, might have to stop this video because I can hear the dog waking up, which is pretty annoying. 18 minus, what have I got? Right, I've got 8/3 times 27 minus 81 minus 8/3 times 8 minus 16. Now, you'll see that we're going to get a negative number for that integral, and then we'll take the absolute value of it. So in here we've got 72 minus 81. So this is -9 minus, and here we've got, let me see, 64 minus 64/3 minus 48/3. I'm pretty sure no one's watching by now. I think you will have hung up the video because I told you the answer, and we know it has to be 11/3. But we get 18 minus -9 minus 16/3. Of course, you could have worked out that integral separately, right, and then put your working back in nicely later on. So we get 18 minus, what have I got, -27. -27 minus 16 gives me -43/3. And we've got 54 on 3, take away 43 on 3, which gives me 11/3. So there you go, Ben, 2 different ways to do that problem. If anyone's got any questions about that, or you're not confident with some of those basic integral results, you will need them for AS, right? So in particular, the top minus the bottom curve one, and the idea about the integral being negative when it's below the x-axis. Thanks for watching, and keep on sending me in your problems, even though I am a little bit behind in the videos at the moment.